Hey, I wanted to get together with you today and talk about something called kinematics. You see the word written out right there. Kinematics means the study of motion. This word kinema is an old Greek word that means motion, and so that's what we're talking about here with the motion of an object. Here's a little car. We deal with lots of cars. We deal with lots of rocks and balloons and balls and any kind of thing that you can think of that will move. You could picture this guy, and he's starting out right here, and he's going to move over to the other thing. So picture this guy traveling from here to there in his little pickle car, and there's some things that we could do. We get in cars and travel all the time. We walk all the time. That's motion. And we can use this idea, this kinematics, to model all that and say, where are we going to be? How long is it going to take us to get from here to Charlotte? How fast am I going if I move this much distance in time? All of those questions are what we're interested in when we talk about kinematics. Now, typically, he's got some speed here, some initial velocity, and we're going to abbreviate that V0. The speed at the beginning of the problem is called the initial velocity, and we abbreviate it V0. That little zero right there essentially says the velocity at time zero, the initial velocity. Over here, this would be the final velocity. How fast is he moving at the end of the problem? And that gets a V, where the V would be the final velocity. The V with the naught would be the velocity at time zero. So you see the difference already there. I need two names for those because they could be different numbers. Some other important things would be the time that it takes to go from the beginning to the end. So we'll put time on there. He's covered some distance, right? He moved from this point over to this point, and so we're interested in that distance that he moves through. We get tired of writing the word distance, or better displacement, over and over, so we just abbreviate that. X will work for now. T could be our stand-in for time. And then there's one more variable that we talk about when we do this, the acceleration, which measures how fast he's changing his speed. That would be A. All right? But try to keep that little picture in your head. Those are the 5 variables that we can and do measure with kinematics. How fast am I going at the beginning and the end? How far did I travel? How much time did it take? Am I speeding up as I go? Those are important questions that we want to model here. Now, this is a little list of the variables, and it's super critical in physics that you look at a problem and you understand what the numbers that they're giving you are, and you want to put those numbers into each little box here that it belongs in. Now, I've already told you the variables names here, the little abbreviations. For distance, we're going to use X. The initial velocity is V0. The final velocity is V. The acceleration is A, and time is T. I always try to do that loopy time, you know, with the little curved tail like that. Sometimes people do T like this and it starts looking like a plus sign. So if you kind of get in the habit of curling the bottom of it, then it doesn't get mixed up and look like a plus sign. All right. I think we've got the meaning of those down, so I won't fill that in. But the units over here, this is a really important part of physics. And if you can learn now to watch the units, then everything will be fine. When I measure distance, I could measure that in feet or inches or miles or yards or cubits or chains or rods or fathoms or all sorts of units. But the one that we like is the meter. We use the metric system in science because it makes sense, because it's a better measuring system. And I think you'll come to love, understand and love it real quick. We abbreviate the meter with an M. All right, so anytime you see 6M, then you know that you're talking about 6 meters of distance. The M tells you that it's a distance. Down here, velocity, in this country, we would measure that in miles per hour. If I'm going 30 miles per hour down the road, that's a velocity. Properly, it's a speed because it doesn't have a direction, but we'll talk about that later. That's how fast we're going. In here, since we're using meters, and we're using seconds, then that would be a meter per second. Instead of a mile per hour, we're interested in meters per second. And so right here, you might see something that looks very much like that. As soon as you see m over s, meter per second, you know it's a velocity. And then the only question is it the initial velocity or the final velocity? All right? So this would also be a meter per second right here. All right? The proper units on acceleration, and we'll talk more about this later. For now, just write down meter per second squared. And the time, of course, is measured in seconds. We've already been working with that. In physics, if you can learn to use the right units and to see what they're giving you, everything just gets a whole lot better. But in general, we always want to use meters, kilograms of mass, and seconds of time. That's for the whole semester. If you can learn to work with those units, we don't need the kilograms until test 2, but meters and seconds, and anything that I can make up out of meters and seconds, like meters per second, meter per second squared, then you're doing all right. If you see something in centimeters, we don't like centimeters, okay? We don't like minutes or hours. We want everything in meters and seconds, and it just makes your life so much easier. All right. Now, the first thing that I want to talk to you about, the first formula that I'm going to put down here, is this definition of acceleration. Acceleration is the rate of change in velocity. What that means is if I'm going one speed and then I speed up and go faster, how fast did I speed up? How much time did it take me to go from the first speed, v0, to the second speed, v? So any of those problems that you see, maybe a problem looks something like this. A car moving 6 meters per second speeds up to 12 meters per second. Oh dear. Let's try that again. Speeds up to 12 meters per second in 3 seconds. And they might well say find the acceleration. Okay? Well, there's nothing hard about that at all. What you want to do is to, I don't know how to get rid of the box, is to look at this problem that they've given you and find the numbers that are involved in it. I'm going to just make a little circle here, which kind of drives me crazy. There it goes. Oh, I see. This guy, did it again. Right here, it's not going to let me circle that, is it? Too close, too tight. Right there's a number, right? That 3 seconds. That's one of the numbers that we're trying to fish out of this problem. Here's another one, 12 meters per second, 6 meters per second, and then over here somewhere it used to say find the acceleration. That's actually another number. So there's 4 numbers in that problem. Physics is a ton of word problems, but they're not hard to do. All the problem does is it just hands you some numbers and gives you a context, hopefully a little bit of an interesting story, makes it a little puzzle that you can kind of figure out. And what I would kind of do here is come in and say I've got 6 meters per second and 12 meters per second and 3 seconds, and then they want this thing called A. You don't have to turn it into that list every time, but somehow you need to know what they're giving you and what they're asking for, and that list is a pretty good way to do it, like that. But the 6 meters per second, 12 meters per second, 3 seconds, I got to figure out what those are. Now, one thing I would suggest is you go right here and you look at the units first. If I see something in meters, it's going to be a distance. If I see meter per second, then it's one of these two. It's either the initial velocity or the final velocity. And of course, time would be seconds down here. So when I look at that list of numbers that I've made, and I see 6 meters per second right there, I know it's some kind of velocity, and this would be some kind of velocity. So I could go ahead and put v's there, but remember we use v0 for the initial velocity. At the beginning of the problem says it was moving 6, then it changed and went to 12. So the initial velocity would be this guy, and the final velocity would be that. All right, that wasn't hard. Just read the problem, figure out what these things are. 3 seconds, I look at the unit, seconds only measures time, so I know this is time right here. And see how easy it is to come over here and you put the numbers in. V, and I look at my list, 12 meters per second. Minus V naught, that's 6 meters per second. I divide that by T, that's 3 seconds. And I do the arithmetic here. 12 minus 6 would be 6. I divide that by 3. I would have 6 divided by 3 is 2. And I've got this unit here, meter per second, on top and a second on the bottom. It's a meter per second. And that's really a good way to write what it is that we're doing here. What we're saying is, with this thing, is that my car speeds up 2 meters per second every second. And that's literally what acceleration means. My acceleration is 2 meters per second, every second, right? And so I can say, well, how fast am I speeding up? Oh, yeah, it's right there. Now, turns out we don't write it that way. What we do instead is, let me show you some of the gory details of this right here. And there's a little bit of a shorthand that we invoke here. When I take meter per second, that's a compound fraction. And so I can rewrite that as meter per second divided by seconds. And if I want it to look like a fraction, I can even go seconds over 1. There's a little invisible 1 down here. It's not going to let me sneak it in. But that's a division of fraction. And of course, when we divide fractions, we invert and multiply. So I've really got this right here, meters per second times. I invert the second fraction, I turn it into a multiplication problem, and now I just multiply across the top. Meters times 1 is meters, and seconds times second is seconds squared. So those are the units that we kind of like the best for that. It's a little bit shorter, cleaner, neater than going meter per second all the time. We would just write this 2 meter per second squared, and that would be the acceleration of this thing. And that's our first little problem that we did. We have a formula, and we use that formula by reading the problem up here, finding the numbers that are in that problem, making a little list or somehow understanding that what these numbers represent, and then we plug them into the formula. All right, there's nothing hard here about physics at all. That's the game. That's what we're trying to do. And we'll have a number of these formulas that we're going to cook up right here and now. Right here, for example, I could take this one. What we're going to do is take this equation right here, this definition of acceleration we just had, and I want to convert it into this. We're going to end up calling this formula number 1 or the velocity formula or something like that. You can call it anything you want. I don't really care. But I want to cook this thing up. We're just going to use some algebra here. The rules of algebra are pretty simple. I can do anything I like as long as I do it to both sides. So what I want to do here, to get this guy by himself, I've got to get rid of the minus V naught, and I've got to get rid of this divided by t. Well, it's most convenient to get rid of the divided by t first. So I am going to come in here with that idea of I can do anything I like. As long as I do it to both sides, I'm going to multiply both sides by t. And then I have a t on the top, which cancels a t on the bottom. A times t would simply be at. And then I'm left with v minus v naught over here on the right-hand side. Okay, I'm one step closer. I got rid of the t. Now I need to get rid of that minus v naught, the subtracted v naught. The opposite of subtraction is addition. So if I come in and add v naught to that side, then minus v naught cancels the plus v naught. Whatever I do to the right, I've got to do to the left too, though. So I'd have that right there, and that leaves me with v naught plus at. That's equal to v. And the only thing we have to do here is just switch sides, right? Let the v come over to the left-hand side, and the v naught plus a come over here. And that in the box is going to be called formula number 1. That's a pretty handy formula. I'm going to look at some examples at the end of this and show you how to use these, how to pick the right one, how to get the numbers and put it in, how to watch all the units and make this happen. But that's one of the important formulas there. Let me put a little star there by that. That's one of the ones you need to get this right. All right, so that's the first one. I got another one here called the displacement formula. You can see at the bottom that's what we're trying to cook up. I want to derive this formula down here. This one takes a little bit more doing. There's a really nice way to do it with calculus that's almost painless, but right here we're going to do something kind of similar. I've got this thing that I haven't written down yet, but let me put it right here, that the velocity is distance divided by time. Now, you know, if you're working with miles per hour, that gives you a velocity. So that's kind of a nice way to see that. But if I were to solve this for x, I could come in and multiply both sides by t, and I'll do that right here. I'm going to multiply the right-hand side. Why didn't you change color? Multiply the right-hand side by t. And I want to multiply the left-hand side by t to keep everything balanced up like that. And you see that the t on the top cancels the t on the bottom, and I've got this expression right here. Let me spin that around for you. X equals vt, like that. So that's kind of an interesting formula there. If you know how fast you're moving and how long you do that for, then that'll tell you the distance that you cover. For example, if I get on Highway 77 and I go 60 miles an hour, for 2 hours, 60 times 2 would be 120 miles that I cover, right? I'd be, oh, I don't know, past Charlotte somewhere. So that's the displacement formula right there. When I take the velocity multiplied by time, I get the distance that I travel. So what we're kind of doing here is we're making a little box. Let me draw a graph real quick for you. If this is the velocity and this is the time, if I'm going a certain velocity, I really dislike how it does that, and I do that for a period of time, I could kind of draw this little box here. I'm going this speed, I do it for this long, and see how I've got all this area in here. Well, let me color that in. I'm trying to cross hatch it. But this space inside here, it's just a rectangle, right? The area underneath that, this would be the height of that rectangle. This would be the length of the rectangle. When I multiply the length times the width, I get the area underneath. So the area of this right here is equal, you know, length times width would be v times t, and that area is the distance that I travel. All right. Now that's what we call constant velocity. I'm not speeding up right there. I'm just going at the same speed for the whole time, and you know, like you would on the highway, for example. On the other hand, if I do change my speed, that's an acceleration. We could start out down here. And I'm going to have to draw this backwards, I guess. Let's say I start at a velocity of 0 here and go up to 20 miles per hour or something, 20 meters per second. Then the same little trick works where I have the area underneath that curve is the distance that I travel. So if I can find this area here, then that would be the distance. Well, that's a triangle, right? Area of a triangle is 1/2 the base times the height. So when I look at this thing, I've got a 1/2. The base down here, the bottom of the triangle is t. So I'll put that in for the base. And the height of this thing would be v up there. But I could have started somewhere else, so I'll put in a v minus v naught here. In this case, v naught was 0, so it kind of works out just fine. All right. So, you know, that area underneath the curve is an important idea, and that's actually what led to calculus. Newton and some other people were thinking about how much area, is there a way I can add up the space underneath that box? And that's where calculus comes from, which is kind of neat. The graph we really want to think about, though, you know, maybe it starts right here and it goes up to there. And I'd like to know the total distance underneath that box, underneath that curve. Well, what we can kind of do here is cut it into two pieces. And I can say, I'm going to come in here and I'm going to have a rectangle on the bottom and find that area. And then I'll have a triangle on top and that area. And if I add those two areas together, oh boy, then I'll have my total area. So that's the thing that we're working on doing here. Again, there's a very easy, painless way to do this with calculus, but some of you are in Physics 201 not doing calculus, and some of you are in Physics 221, and I'll have another video on how to do it with the calculus like that. But I want that total area, let's call that area 1 plus area 2, where this can be area 1 right here, and this will be area 2. If I add those two pieces together, this and this, then the algebraic derivation of this thing's not too bad. I got V naught t. I was going some speed at the beginning. I kept going that same speed. And then right here, I've got 1/2 t v minus v naught would look like that. All right, and this may seem a little bit weird right here, but remember that definition of acceleration that we had, a equals v minus v naught? That almost looks like this part, but it was over t. So I'm going to kind of pull a sleight of hand here. What I'd like to do is multiply top and bottom by a t over t. You notice that those cancel out and just give me 1, so I didn't change anything here. But what I want to do is to take the v minus v naught over this t right there. That's going to make acceleration. If I got a v minus v naught over t, I can replace that with an a right there. So that's the little trick that we're pulling here. And that would be v naught t. Didn't do anything to the first term. Here's a 1/2. Here's all that stuff that I circle up right there, and now I'm calling it a. And I've got a t times the second t over here would be t squared. So that's my total area. And we've already said that that total area represents the displacement, the distance that we travel. And so that is formula number 2. That's an important formula. Anytime I want to know how far an object goes, how much distance it travels, if you can tell me the velocity it was traveling at times the time and how fast it was speeding up, I can get you the distance there. So that's kind of neat. All right. Next formula is called the velocity squared formula. This is going to be formula number 3. There's only 3. All right. With these 3, you can do everything that you need to do here. And you remember that we've already got 2 formulas. Here's the first one, and here's the second one over here. Formula number 1, number 2. So what we're going to do is kind of mash these 2 together. This is laid out for us here. You can see that I want to solve it for t. Well, t is right here. I want to get that by itself. So the first thing I'm going to do is subtract v naught from both sides. Again, I can do anything I like, as long as I do it to both sides. V naught minus v naught would be 0. I'd have a v minus v naught on the left. Nothing but this a times t on the right. I want to get the t by itself, so I got to get rid of that multiply by a thing. So I divide by a over here. The a's cancel, and I'd have v minus v naught over a equals t. All right, so that was step 1. What we want to do now is to plug that in over here. So everywhere that I see t, I want to take v minus v naught and bring it up and up and up and over here. And I want to drop it in right there. And I also want to drop it in, ooh boy, I want to drop it in for this guy too. Right there, I got 2 t's. You know, t in the first term, t in the second term. So I want to replace both of those with this thing I just cooked up. And that's going to look like this. It's going to get a little bit messy here. I apologize for that. But it's just algebra. We like algebra. V minus v naught over a. Replace that t. Here's the other one. 1/2 a v minus v naught over a, like that. And don't forget to square that thing. These squareds love to get lost, and that just messes up everything. So don't do that. All right. I'm going to take care of that squared first. Let's leave this guy alone. I'm going to leave the 1/2 and the a alone, but I'm going to square this thing right there, v minus v naught over a. Now, if you need to, you can come in here and write that whole thing out. You know, here it is one time. I want to multiply it by itself. Would look like that. But basically on top, I need to take v times v, then v times negative v naught, and negative v naught times v, and negative v naught times negative v naught. Remember the FOIL method? That's all we're going to do here. So that's going to turn into a v squared minus v naught v minus another v naught v plus v naught squared. And then downstairs, I've got that a times the a, so that's going to give me an a squared right there. All right. I'm going to let this a cancel one of the a's in the denominator like that. And let's see if we can't simplify this. While I go to this next step here, let's distribute. Let's take this v naught times v and the v naught times the negative v naught. So x is equal to v naught v minus v naught squared over a. Let's pull that a out here. Well, we'll just put it all together. How about that? I got that 2 on the bottom times this a would give me a 2a right there. Just going across the top, you can see that these two terms will combine. And we'll just put those together down here. Oh, what's happening? Where'd my pencil go? So this will be v squared minus 2v naught v, adding those two terms together, plus a v naught squared, like that. You can see I've got two fractions. I'm trying to add those two fractions together. I need a common denominator, right? So all I have to do is get 2a for both of these things. Here's a 2a. This one's only got 2. So I need to multiply this by a, and I need to multiply up here by a, like that. All right. And once I have done that, then this will go together very nicely and get me where I want to go. So let me get my color straightened out again here. I got x having a common denominator now of 2a. I can put that down here. Distributing on the top, a times v naught v. I already had an a there. I'm sorry. Yeah. Let me take all this back. I did something foolish here. I put a 2 down there. It wasn't a 2 at all. It was an a. I'm going, something just doesn't look right here. Let me scribble that out and put the a. So this is not a 2. It's an a from right there. So I don't multiply top and bottom by a. I multiply top and bottom by 2. Already got the a. What am I thinking? Okay, but I do have to remember to distribute that like that. All right, now it's looking better. Now I've got a 2a everywhere I need it, and that gives me a common denominator. So right here I'd have that common denominator on the bottom. Working across the top, I distribute the 2 to the v naught v, it would be 2v naught v. And then I've got negative 2v naught squared. And then I come across, I got the plus v squared minus 2v naught v plus v naught squared, like that. All right, and you can see there's some stuff that cancels out here. There's a positive 2v naught v and that negative v naught v. Those are going to cancel each other out, so those are gone. Right here I've got some v naught squareds, negative 2 of them. Over here I've got plus 1 of them. So that gets me to negative v naught squared. The only thing left is that plus v squared. It's all over 2a, like that. If I were to multiply both sides by the 2a, then I'd have 2ax equals negative v naught squared plus v squared, like that. And you can see if I add this term to both sides, then all of a sudden I've got myself v squared equals v naught squared plus 2ax. I also flipped it as I did that just because I'm out of room here. This thing doesn't let you have any more space. But that's the derivation of formula number 3. And man, that's a really nice one right there. That one gets a star and a rainbow, because that formula is pretty handy right there. The nicest thing about this formula is that time does not appear in that formula. Here's all 3 of them together. Those are the big 3 formulas. Formula number 1, number 2, number 3. We derived all 3 of them, so I hope you understand where those come from. But that will do everything on test 1 right there. You need to know those 3 formulas. I don't expect you to memorize them, because that's not what physics is about. This is not a memorization game. This is a problem-solving game. They're going to give you a problem and expect you to solve it to get the answer. So you need to have those formulas. I let you bring an index card to the test, so I'd go ahead and put those on your card. Those are going to be important. All right. There's one other way I'd like you to think about these things. Remember we said these things have units? So right here, when it has a V, that's a meter per second. If I just kind of put the units there, this V naught is also in meters per second. The A is in meter per second squared. And the time right here, multiplied by T, that would be measured in seconds. And see how this second on top is going to cancel that second on the bottom? Not both of them, but one of them. So I'm going to have some number of meters per second on the left-hand side. And I've got some meters per second here, some more meters per second there. That's going to give me meters per second. And the units match up. They work. That has to happen for a formula to be valid. If the units don't work, then your formula is no good. And you need to watch those units and make sure they're doing what you're supposed to do. That is the easiest way to tell that you've made a mistake. When you see the units mess up, you need to throw your paper away and just start over. All right, or go back and find your error or something, because the units will just scream at you, hey, you made a mistake. Okay, so watch out for that. All right, but write those things down. They're important. Here are some examples real quick. Find the distance a car that is accelerating 1.5 meters per second squared will move in 20 seconds if it started at rest. They're all some variation of this. And of course, I've put the 3 formulas down there at the bottom for ready reference. Right? There they are, the big 3. But there are 5 variables that we are interested in measuring. And here's all 5 of them. When I read the problem, I'm trying to fill in those boxes, find the distance. Oh, that's what I'm looking for. So I'm going to put a question mark there. A car is accelerating at 1.5 meters per second squared. I can look at the units right here, meter per second squared. I know that's the acceleration. The problem also tells me it's the acceleration. So I feel pretty safe coming in here and going 1.5 meter per second squared is my acceleration. Right here, 20 seconds. Seconds measures time. So I'd put that in the list for T. Okay? This one right here is one you kind of got to watch out for. It started at rest. That's a way to say that V naught equals 0. At the beginning of the problem, the car was not moving. It was at rest. So that would be 0 meters per second right there. You need to do that on every problem in physics. If you're an engineering student, you need to do that with every problem in engineering class. This is really important to be able to do these problems. You just put the numbers in the right box. Okay? Then what you do is you come down here and you say, I need a formula that has that set of variables. See how I don't care about the velocity? They didn't give me the velocity. They didn't ask for it. We don't care. All right? I need something with X, V naught, A, and T. So I just start looking at it. Oh, wait a minute. This one's got the V in it. I don't want V. I don't have this. I got the V naught and the A and the T. Oh, I could get V if I wanted it. They don't want V. All right? So this is not the formula that we want. And we go on to the next one. How about this one? X. I'm looking for X. Oh yeah, I got V naught, I got T, I got A, I got T. See how I can solve that? That formula will work for me in this case because the 4 variables that I have are all included right there in that formula. Let's just try the last one here just to kind of get a feel for this. The V, the velocity, the final velocity, I don't have it. I don't know what it is. That's a big question mark, right? V0, got that. A, I got that. X, oops, I don't have that. That one has 2 question marks. That's one equation with 2 unknowns. There's no way to solve that problem mathematically unless you have a second equation, a second formula. Okay? So the bottom one doesn't work. The top one doesn't do what I want. That one in the middle is the one I want. You need to pick the right formula every problem just like that and write it down. Just go ahead and copy the whole thing. X equals V0 t plus 1/2 AT squared. Every time you copy it, it gets a little bit further down in your memory, and you're good to go. I've got all my numbers listed over there. The V0 is 0 meters per second. The time is 20 seconds. The 1/2 times the 1.5 meter per second squared. The time was 20 seconds. Don't forget to square it. It's right there. Okay? That's easy to get lost. 0 times 20 is, oh man, 0 times 20 is 0. Okay, so that's gone. And then I can just pull up my calculator and put this thing in. Move that guy over a little bit. Okay, so you need to have some kind of calculator. The TI-83, 84, 89, whatever you like is fine. It should have a sine, a cosine, and a tangent button. It should have a square root functionality. Should have scientific notation on it. As long as that, I don't care if it graphs or not. That's kind of useless. But if you wanted to start at the beginning and go 0 times 20 plus, for the 1/2 I usually do 0.5 like that. You could also do divided by 2. But times 1.5 times 20, and don't forget the squared. It's right there. There's your squared button. Okay, and there's your answer. It goes 300 somethings. Okay, I write the number down. The number by itself means absolutely nothing. It has to have a unit so everybody on the planet can tell what it is that you're measuring. Well, let's see what the unit would be. Right here, I got meter per second squared. All right, 1/2 doesn't have any units. This was, if you want to do it, there's seconds, which on top, I can't get there. This second on top is going to cancel that second on the bottom, so all I have left is meters. And I lost my pencil. Come back. Okay, so I got meters in the first term, although it's 0 meters. All right, right here's the meter per second squared. There's a second which gets squared, so that's going to turn into second squared, and then the second squared on the top cancels the second squared on the bottom. There's nothing but meters there. 20 squared would be 400. Half of that would be 200. 1.5 times 200 is 300. And so you can see how the calculator came up with 300. But more importantly, I got meters plus meters, which would be some number of meters. I have to have a unit right there. And you really should get in the habit of going through and saying these seconds cancel and those seconds cancel, those seconds squared, and I got meters, right? Make sure that it does right. When it doesn't do right, you know you did the problem wrong. All right, here's another one. I got a car moving 4 meters per second. At the beginning of the problem, the units right there tell me that that's a velocity, so I'm putting that down for 4 meters per second. It accelerates. It says it's acceleration. The units say it's acceleration. I put a 2 meter per second squared right there. This is a velocity because the units, I know it is. Meters per second, it must be the final velocity. I've already got an initial velocity. They want to know the time. Okay? See how I don't care about x this time? They didn't give it to me. They don't want that number. I don't need it. Okay? I need a formula that has those 4 in it. And the first one looks pretty good, doesn't it? I've got a V0 and a V and an A. They want T. So I'm going to write that guy down. And looks like we want the time. Now the last one we didn't have to do any algebra on because it was already in the right format. Here that one is, right? They said, what's x? X was already over here all by itself. But that's not the case this time. They're saying, what's t? But t is tangled up with all this other stuff. So I need to do some algebra here to get that straightened out and then put my numbers in. I think you'll find that to be easier, better, quicker, more convenient. I'm going to subtract V0 from both sides because then I would have my V0 here is going to cancel the V naught right there. Plus V naught minus V naught adds to 0. And that's going to give me, on the left-hand side, I'll have V minus V naught. On the right-hand side, I'll have AT. Okay? So we did one step there of algebra to get rid of some of that. I want the T by itself. Got to get rid of that A. These two are multiplied. Do the opposite. The opposite of multiplication is division. So I need to divide both sides by A. And the A on the bottom is going to, where is that stupid pencil? The A on the bottom is going to cancel the A on the top. But whatever I do on one side, I have to do on the other side. So I've just got the T by itself now. That's the whole trick. Get the T by itself. I'm going to spin it around. T is going to be equal to V minus V naught over A. I've got all the numbers. I put them in. 12 meters per second minus 4 meters per second, all divided by 2 meters per second squared. Okay, now notice the squared is on the seconds. It's not on the 2. It's not on the meter. It's just on the seconds there. So be careful with that. But I could do several things here. I could come up with my calculator and do this all in one fell swoop. I noticed that 12 and the 4, that's subtraction. This needs to happen before I divide by 2. I got to straighten out the top and then divide by 2. So let's put some parentheses when we do this. I'm going to hit the parenthesis button. 12 minus 4. Close up the parenthesis. Now my numerator is closed. I divide by 2, and I get 4 right there. Okay, that's the answer I should get. If you want to go in slow motion on that, do it by hand. 12 minus 4 would be 8. Still got the 2 on the bottom. 8 over 2 is 4. All right? So just make sure that you do that. What people like to do, I think I said this on the other thing, was to leave out the parentheses. They go 12 minus 4 divided by 2. Right? See how you get a totally different number? The calculator wants that in a certain order. It's remembering order of operations, and it says division is more important than subtraction. 4 divided by 2 would be 2. 12 minus 2 is 10. So learn how to talk to your calculator, and it'll be a whole lot easier for you. All right. The question now is, what's my units? What for what? Now I know over here it's supposed to be seconds because I'm looking for a time, and I guess you could just come in there and write seconds. Okay. But this really doesn't take that long. I've got meters per second on top. I got meter per second squared on the bottom. That's a compound fraction, so I need to invert and multiply. The meter on the bottom is going to cancel the meter on the top. The second on the bottom is going to cancel one, but not both of the seconds on the top. And I'm just left with a second right there. So the right answer would be 4 seconds. And taking that extra half second of time there to look at the units and make sure that they behave themselves makes all the difference in the world. All right. Here's one. Car moving 2 meters per second. That's clearly the initial velocity. It accelerates. Must be a meter per second squared of acceleration there to 12 meters per second. This is looking an awful lot like the last problem we did. Oh, wait. Find the distance. This time we're looking up here. Okay? So this one does not have time in it. I want something that uses these 4 variables. So I get busy on my list and I go, wait a minute, this one's got time. That one won't do. This one's got time in 2 places. That won't do. I guess I'm going to have to use that bottom one. And that's what I would do right there. So I write it down. V squared equals V naught squared plus 2AX. I want this guy by itself. Let's subtract V naught squared from both sides. And then I can divide by the 2 and the A. And it'll look like that. And I've got all the numbers. So I'd come in here and say 12 meters per second. Don't forget to square it. Minus V naught. Over here on my list, that was 2 meters per second. And I got to square that one because it says 2. Down here I've got 2 times A. That would be 2 meters per second squared. The squared's just on the second, not on the whole thing. That's going to be the distance. And if I were doing this on the calculator, I would want to do a couple things before I got busy pushing buttons here. The first thing I would probably do is remember to hold together that numerator. All right. So that would look like this. I'm going to put some parentheses over here to make sure all this happens. And then I need to divide by 2 and divide by the second 2. So one way to handle that is to come in here and put some parentheses around that 2. And when I go to my calculator, then I can come in here and say parenthesis 12 squared, don't forget squared, minus 2 squared, close it up. That's my numerator. That's the top, divided by red parenthesis 2 times 2, close it up like that, and that should work just fine. 35 meters is what I'm going there. How do I know it's meters? Well, up top I'd have meters squared over second squared, right? Not only does the 12 get squared there, but the meters get squared. Everything inside the parenthesis gets squared. And then here's meter per second squared. The meter gets squared, the second gets squared. On the bottom, though, I've just got meter per second squared like that. Compound fraction, I invert and multiply. Meters squared, second squared times, inverting second squared over meters. The second squared on the top cancels the second squared on the bottom. The single meter on the bottom cancels one but not both of those. So I'm just left with 35 meters. All right, and the units worked out. Everything's good. All right, so that is kinematics. Those 3 formulas at the bottom are critical. You need to write those down. You need to know how to work those things. There is a kinematics LOP in D2L. If you go and you click the kinematics LOP and just start working those problems, doing them exactly like we did right here, and it tries to kind of coach you through that. And we will do some more of these on Zoom meetings in class and whatever. But that is the big idea and most of what you need for test 1. So thank you for your time today. Have a good day.